Part 2, now we're on 8.1, exponential functions. We're doing exponential functions this section, and then 8.2 is the actual derivatives. We're kind of talking about how exponential functions grow in terms of their limits, what they approach, and whatnot. Okay, so first off, an exponential function, let's just get back to the basics, is in the form of b to the x. Okay, with b being a positive constant. Okay, a positive constant for now. Okay, we're going to kind of talk about they're going to talk about the reason that, let me just go through it here instead of trying to explain it. Okay, so we have define b of x if x is a rational number, but we can also define it essentially when it's not rational. Like we can do 2 to the root 3. If you put 2 to the root 3 in your calculator, you'll get a decimal, and it actually lies in that line. So what they're going to go through this next slide is we're going to talk about why that's possible by looking at it from both sides of root 3. Okay? So that's what we're going with. But anyways, this is kind of the rough graph of 2 to the x, what that looks like. Okay, it makes sense because what's 2 squared? 4. So that's why that's right, 4. Okay, it's just growing just like you would with an exponential. It's growing exponentially. Exponentials grow really fast because they're exponents. Okay, all right. So let's go to the idea here with the rational part versus irrational. So we want to enlarge the domain. So we want to say it's for all real numbers instead of just rational versus irrational. So what we're going to do is we're going to look at both sides of root 3. Root 3 is between 1.7 and 1.8. Okay, it's between 1.7 and 1.8. All I'm doing right now, again, don't let me lose you. All I'm doing right now is we're just kind of proving that rational or irrational numbers are on this exponential. Okay, so 2 to the 1.7 and 2 to the root 3 and 2 to the 1.8, kind of the same relationship, okay? Because we know that 1.7 is smaller than root 3. We know that 1.8 is bigger than root 3, okay? So when we look at this table with it, we can even make it even more precise. We can get it really, really, really close to this outtake right here, where we can see root 3 is between 73205 and 73206. Okay, we can get it down to that point. So we know it's right there. Okay, so it can be shown that there's exactly one number that is greater than all the numbers. So this is just showing you, if you have 1.7, you can keep making it greater by adding stuff to the end of it. And conversely, you can also do it with the smaller numbers. So 1.8, 1.74, 1.73, etc. Keep getting smaller. These are the endpoints right here that is underlined. Again, we're establishing that the irrational numbers actually are on our line. Okay? They are on the graph.
What does it mean in the definition before when it said it is defined as x is a rational number?
Right, that's the definition of an exponent, but we're showing that with calculus we can use our rationals.
Okay,
so like,
really
right, like that's the basic for an exponential, but with finding limits and like with doing our derivatives, we're okay with having irrationals is what we're showing. That'll fall on the line. Because root 3 is a number, right? So if we put root 3 in there, we put that in our calculator, it's going to kick something out. It's not going to be confused. Okay? Okay, so we define 2 root 3 to be this number. Using the above approximation process, we can compute the correct 6 decimal places. So the point is, we put 2 root 3 in our calculator, we will get that. Okay, it kicks out a number, it's a real thing. Okay, in general, if x is any irrational number, we can define 2 to the x, or b to the x, which is the definition like Dara was just saying, b greater than 0, in a similar manner as a limit of approximations. So I guess a better way to say it is that we can't get an exact. So 2 root 3, we're never going to get an exact answer because irrationals go forever, right? Irrationals are like non-repeating decimals. So whenever we get something like this, it's going to be an approximation because we're not going to be able to get it to the exact number unless you leave it. Okay? All right. So it can be proved in the laws of exponents are still true when you're using them. So we can still do our laws of exponents with it, and we'll get to that when we're actually doing examples rather than just explaining it. Okay, so let's talk about actually in terms of how they grow. So we're familiar with this is y equals 2 to the x. That one takes off. So what would you say if I said y to the 2 to the x going to negative infinity, what's it approaching? It's approaching 0. Very good, right? So it's approaching 0, right? And if I said it's going to infinity, what's it approaching? Infinity. Very good. Does that make sense? So 2, okay, we're going to get to the definition in a second. The one for 2, it approached infinity and then negative infinity. Very nice. Okay. So looking at this example. So draw these, just sketch these graphs here. So what does 3 to the x look like? Okay, so just sketching 3 to the x. Okay, so you probably only need to do 1, 2, 3 on both sides. It's going to take off quite quickly. Okay, and then I want to think about what the difference of 1/3 to the x looks like. Three to the x should look somewhat like the 2 to the x. Okay, maybe a little steeper because it's a bigger base. So 3 to the 1 is just 3. Okay, and then you'd have 9, and then you have 27. Okay, it just would keep going up. Okay, what's 3 to the negative 1 equal to? So I can do negative 1. 1/3, very good. Okay, and then conversely, the next one would be 1/9, 1/27. So it would keep getting smaller here. So you can kind of see, kind of just takes off something like that. That'd be your y equals 3 to the x. Now, is the 1/3 going to be similar or different? So, well, let's just think about the same thing. I mean, yeah, similar is good. Okay, with exponentials, with just x at the top, they're all going to cross through where? 1, right? They all have to cross through, I'm a little off, but they all have to cross through 1. Why is that? Because when you put a 0 in for x, anything to the 0 power equals 1, no matter what the base is, right? So we know that's going to be a spot for all of them. Okay, so let's look at 1 there. So what's 1/3 to the 1? 1/3. What's 1/3 to the 2? 1/9. So essentially it's what? Yeah, it's flipped of this. Over here we are 1/3, 1/9, 1/27. This is 1/3, 1/9, 1/27. Over here it's going to be the opposite. It's going to be 3 and then 9. So it takes off in this direction. Okay. So we're going to get to the definition in a second of what that means for us. But so what's this one's limit approaching infinity? 0, and approaching negative infinity. Infinity. Okay. So that's going to be something we'll need to know for when we're doing our understanding derivatives with the limits part. Okay, so here's kind of an illustration. Okay, here's a bunch of different examples. You got your 1/2, your 1/10. Okay, you see they're coming down to the right. Okay, you have your bases that are 2, 3, 5, and 10. They're all growing upwards. Okay, and then you can see they're all knotted here at the 1. Okay, they're all knotted at the 1 there because no matter what, to the 0 power, it's going to be 1. Okay. Okay, and we see from these graphs there's basically 2 types of exponential functions, and that's kind of the point off our last example. There's 2 types. We have the ones that are going up to the right and the ones that are going down to the right. Okay, what do you think that is? Do you want to make a guess to what's causing that, or what it would be? Yeah, like we have 2 types. We have these 2 types and then these 4. So based off what those bases are, what those numbers are, do you think you can kind of come to a conclusion of what you think the rule is? Close, yes. Between 0 and 1. We still want to say positive, so it's that fraction idea. So a fraction less than 1. No, because we don't want to have negatives for our base. If you have negative for your base, then things get weird because you start doing that flip thing, right? So fractions less than 1, bigger than 0, give you the downward guy. Anything bigger than 1 gives you the upward. Okay, because anything bigger than 1 exponentially is going to grow fast, right? Anything smaller than 1's a fraction, as you get bigger, it actually gets smaller, 1/3, 1/9, 1/27. It keeps tailing off. Does that make sense? So that is the definition, so good. Okay, all right, so here's the definition for this one. This is the first one. So when b is greater than 1, the limit as x goes to negative infinity is 0. Okay, we knew that right here. It's going to 0. Okay, red boxes are usually the ones I'd write down. And then for that same b greater than 1, when it's going to infinity, it goes to infinity. It's just going up infinitely. Okay, remember, going to infinity means to the right. Going to negative infinity means to the left. To your negatives infinitely. The first part. So this one says, we're talking about whenever b is bigger than 1, so 2, 3, 4, 5, if x is going to negative infinity, so if x is going in a negative direction on that graph, what's it approaching? It's approaching 0. So it's approaching 0. Okay, second one here. All right, so then the conversely is if, we just talked about it, when b is bigger than 0 but less than 1, it's the opposite. So as x approaches negative infinity, it's going to infinity. So when it's going to negative infinity, it takes off. Okay? When it's going to infinity, it levels out at 0. And I know this is simple, but don't forget this, because a lot of people forget this when they're doing their exponential work, and they miss things just because they forgot, or they just didn't think about it logically. So now we're going to look at another example here. So example 2. So it says use a graph of y equals 2 to the x to sketch the graphs of the following functions. So I want you to think about what would change. Okay, so how does the 3 plus affect it? How does the negative 2 to the x affect it? Okay, so easily just plug in numbers and see what happens. You don't have to graph it and change it. Just see what happens. Okay, we can do them on the same graph. Okay, so think about how does a 3 plus 2 to the x affect it? Yeah, everything shifts up 3. So we know it's supposed to cross at 1, but with this guy it's going to cross at 4. Very good. So then what is essentially 3 plus 2 to the x's horizontal asymptote then? Like what's it approaching? Not approaching 0 anymore. Approaching 3. Good. It's going to go like this, right?
Wait, why did it go to 4?
Because this 3, see how it's 3 plus? So watch, if I put in a 0 here.
Oh, we put in 0.
Yeah, 0 gives me a 1, 3 plus 1 is 4, so it moves it up 3. It's a vertical translation, right? Okay, for the second one, what changed with the second one? So if I put in a 2, or let's put in a 0. If I put a 0 in, what do you get? Negative 1. Okay, if I put a 1 in, what do we get? Okay, so it essentially flips it. It's going to keep taking off in that direction. Okay. So flipped it, the negative, just like we did with parabolas, the negative flipped, okay, that exponential graph over. Any questions there? Okay. All right. Just got a couple more here. All right. So for 3, use a graph of y equals 10 to the x to sketch the graph of y equals 10 to the x to the minus 1 minus 2. So we want to figure out, we're going to look at 10 to the x, and we're going to look at 10 to the x minus 1 minus 2. And we want to look at how those relate in terms of the graphs here. So let's do some color coding here. We'll do this one with the green, this one, the change with the blue, and we'll keep our graph black here. So 10 to the x we can do, that's pretty simple. We still know that still goes through here. Okay, and we know that it's going to be growing quite quickly. It's pretty steep here. And it's be at like a 1/10. So okay, so that's what the original looks like. Oh, I'm supposed to do it in green. Okay, so our original. So how does it change? Okay, it moves down 2. Okay, good. So we know it moves down 2. So 1, 2, and right what? Why is it right 1? Because it shifts right. This up here causes a horizontal movement because if I put a 1 in here, that gets me to 0 now. The 0 creates that 1 minus 2, so it's going to be, which you're right, so it's going to be right here. So it was supposed to be right here. It moved down 2, right 1. That's where that point moved to. It moved to the right because, how do I make this 0? I put a 1 here, right? So putting a 1 here moved it positive 1. Because, okay, let's see how else we do this. Okay, if we put a 0 in here, that's now a negative 1. So where is negative 1 usually at? That's to the left one. So what happens is everything's been shifted 1 to the right, opposite of the movement of the, just like with, here, let's go with this. Just like when you're doing parabolas, like how you have, like x plus 3 squared moves your parabola left 3 because it's to 0. What makes this 0? A positive 1, so that's our movement. Does that not help or no? Negative 3 for this one? Or this one? Let's see here. Let's just test some points. So we at 1, that's where this is at. At 2, 2 minus 1 is 1. Right, so yeah, it'd be at negative 2. Right. No? Hold on. The asymptote, because it's 10, it is growing up. So let's do this here. Hold on. If I put 2 in, that gives me 8. So that's going to give me 10 minus 2 is 8. Right here. So then, actually, yeah, negative 2 is asymptote. So then if we put in 0, yeah, if we put in 0, that gives me 1/10. 1/10 minus 2 is a negative 2/10. So, no, negative 1 and, sorry, I'm just plugging things in my head. But yeah, so it's gonna, this is the asymptote. So it comes through, yeah. That's how that one grows. It's still a 10, so it's still going to grow the same way. So it's going to have a little shift to the right. That's all it did was shift to the right 1 and went down 2. If it's, yes, if it's bigger than 1. Okay. All right, and then we're going to think about this one. We'll take a quick break, and we'll finish. We'll be done with this one already, which is good. Okay. All right, so think about this one. Okay. So we want to find a limit as x approaches 3 from the left of 1 over x minus 3. Okay? Now, when you're approaching numbers from left and right, well, we can't, remember, we always want to say, can I just plug a 3 in? No, because I get 1 over 0, right? So then what do we want to try? What do we want to do? Yeah, numbers really close to that. So what's something really close to that? 2.9 is a great one. So let's try 2 over 2.9 minus 3. Can somebody put that in their calculator and tell me what they get? It's going to give you a quick indicator of what it's approaching. 1 over, yeah, make sure you put brackets. What's that? Yeah, this is a power. Yep. Sorry, that's horrible. Yeah, it's 2 to the, so 2 to the 1 over x minus 3. And we're trying 2 to the 1 over 2.9 minus 3. Okay. You gotta put brackets on the bottom too. So what is that 0.9e negative 4? So it's like, it's something like this. So then what would your guess be? What's it approaching? 0. It's 0. So your answer would be 0. It's approaching 0. And you can keep trying that. Like if 2.9 wasn't obvious, try 2.98. That's not obvious. Try 2.99. Just keep going until it makes it obvious. Yeah, Mark? Okay? Any issues with that? So right now, this whole lesson was just to look at the behavior of exponential functions, understanding how they're growing from positive and negative infinity. Okay? So the gist of it, numbers bigger than 1, it's going to be growing in a positive infinity to positive infinity. If it's between 0 and 1, it's going to be going the opposite way. Okay? All right, so that's it for this one.